Hello, I'm Han from NVIDIA. Today my topic is scale OVN to next level. I have some overview for scale challenges and then talk about some important optimizations for OVN control plane, primarily for OVN controller, and then some thoughts on incremental processing. Let's look at OVN control plane. There's some bottlenecks. For these bottlenecks, we have a lot of improvements already from the community over the years, and there's more improvements ongoing. And in this talk, I'll be focused on the OVN controller because in NVIDIA, we care more about the OVN controller. It's because we're running OVN controller and OVS on smart NICs, which usually has less CPU and memory resources than the host. The first thing I will talk about is trade IP mobility for scalability. Let's look at some background. There's some best case scenarios where lots of small isolated tenants exist in the cloud. Within each tenant, the workloads need to communicate with each other, but between the tenants, there's no communication at all. So that means on each node, there is only very limited number of logical topology, and the size of data to be processed by each OVN controller will be very small, and there's not much processing power, processing pressure required. But in reality, there can be very large tenants. Each tenant can contain huge amount of workloads, which can span across most of the nodes in the cloud. In this case, for each OVN controller, that means it has to process almost the whole topology of the southbound database, which creates the scale problem. Let's look at what data is required by each node, by each OVN controller. To support IP mobility, basically any IP can be located anywhere in the cloud. That means each node need to know how to reach to every individual logic switch port in the cloud. Basically, on the source node, we need to have all the logic flows that can find the destination logic switch port, and then all the port binding information that tells the exact physical location of the destination logic switch port. So in this diagram, work nodes on the node A need to send some packet to work nodes in node B. The packet will go through some logic pipelines, logic switch and routers, and these pipelines are executed as the OVS flows, which all happens on the node A side, in fact. To reduce the size of the data that need to be maintained on the source side, we use the approach called pin logic switch to nodes, basically to trade the IP mobility for scalability. We assign subnets to the nodes and contain subnets with node level logic switches. So on the source side, we only need to use the subnet information to find the destination node and send the packet there through tunnel. And on the destination node, then use the individual port binding information to delete the packet to the virtual interface. In this way, the size of the data need to be maintained on node A is much less. But we're sacrificing IP mobility because IP address can be moved from one node to another node only in a block level instead of individual IP level. To implement this in OVN, we don't have to have any big change to the pipelines, but instead we can reuse the existing distributed gateway port mechanism to achieve something very similar and effectively pin logic switches to node. A distributed gateway port is a logic router port with gateway chassis set, and originally implemented for layer 3 gateway, but here we use it for scalability. Each distributed gateway port has a non-distributed part, which is called chassis redirect port, which has a port binding on the chassis specified. So in this diagram, there's a work node on node A that need to send the packet to work node on node B. Node A and node B each has its own node level logic switch. Of course, also node level subnet. And both logic switches are connected by a single shared logic router. When packets go through the logic switch on node A side and enters into the logical router ingress pipeline, according to the routing information, for the destination subnet, we find out the output port, which is the distributed gateway port with chassis set to node B. So that means there's a port binding for its corresponding chassis redirect port that's located on node B. So the packet will be redirected to node B and this phase through the tunnel and continue the processing there for the egress pipeline of the logic router and then the node B side logic switch pipelines. Finally, according to the port binding on node B of the virtual interface, the packet is delivered. Then here we can see that on the source side, only the local logic switch and the shared logic router need to be maintained and processed by the ovn controller, but not the remote logic switches. This largely reduces the size of data need to be processed on the source side. And for this to work, we had some enhancements for the distributed gateway port. Firstly, to avoid pulling all the data to the source node, we should not flood fill local data paths across distributed gateway port boundary. Basically, this is a generic implementation that doesn't have to be used only for the topology shown above here. So in the diagram at the bottom, without the change, the ovn controller will pull down all the information from sourcebound DB for all these connected logical pipelines. But with the change, it will the flood field will stop and the distributed gateway port boundary. Basically, only the green part will be pulled down for processing by this ovn controller, but not the gray part and anything beyond. And the second one is about supporting multiple distributed gateway ports per logic router. This feature also is required for gateway use cases. And Nutanix folks and I were cooperated together to implement this. Now let's look at ovn-kubernetes, which is a perfect use case for the design we just discussed, because it already has node level logic switches and subnets, which connected by a single shared cluster router. The scale problem exists here is every node needs to know all the logic switch information for all the other nodes and all the port binding information for every logic switch port. And because of this, each node has to process huge amount of data. And we had implemented ovn monitor all option for ovn controller to avoid to disable the conditional monitoring, to avoid overload the sourcebound database, because the monitor condition is already so big. And now with distributed gateway ports, each node only needs to know its own node local data path and shared cluster router and join switch, but not any other node level logic switches. And it's only need to know its own port bindings located on the node, instead of all the port bindings across the cloud. Because each node has only very limited information now, then we can re-enable the conditional monitoring so that each node will pull only a very small amount of data from the sourcebound database. The benefit is huge here. Firstly, ovn controller recompute will be much faster. Although we have implemented incremental processing for ovn controller, but there are still many scenarios requires full recompute. For example, ovn controller or OVS restarts, or adding deletion nodes and some other changes that cannot be handled incrementally. And even for incremental processing, it's much faster because there's less number of data paths and port bindings to process, and especially when data path group is enabled, there's only one local data path now for each data path group. And conditional monitoring can be re-enabled because each node needs to only care about very small portion of data of southbound server. Here, southbound database server may have some higher cost for filtering because of enabling conditional monitoring, but it has a much lower cost for data transferring. For ovn-controller, ideal cost will be much lower because the data to be processed is much smaller. And there are also a huge amount of memory savings. Firstly, less amount of OVS flows to maintain for both ovn-controller and OVS. And secondly, the southbound IDL data is much less with more conditional monitoring. Here is a scale test result. We simulate a topology that is very similar to ovn-kubernetes. And the result shows both CPU and memory savings. And the latency is almost 90% less than before. And the memory savings are around 80%. There can be some further improvements. Basically, if you notice, there's still one flow that is per logic switch port on the shared logic router pipeline. And the goal is to make it big O n equals number of nodes instead of logic switch ports. Now, the next optimization I want to talk about is about logic flow tagging. There are some pros and cons for the logic flow concept. The benefits are, firstly, the intermediate representation is helpful for understanding the flows and very helpful for troubleshooting. And it's also centralized processing for common tasks instead of repeating the computing on every hypervisor. But there's also some disadvantages. Firstly, the extra layer introduced some extra processing. The logic flows has to be reprocessed and converted to open flow rules by each ovn controller. And secondly, the structured data in northbound database has been converted to logic flow matches, which is basically strings. And that means some metadata has been lost. Those metadata could be helpful for ovn controller to optimize the processing if preserved. An idea was to remove the logic flow layer completely, but in fact this has to be evaluated more carefully because it's almost rewriting OVN, which is a huge effort. And there's something it cannot solve. Basically, the string parsing will still be needed for some of the tables, like echoes, QoS, and logic router policy. The match part is all string-based, so the parse cannot be completely avoided. For the metadata preserving, at least we can do something here. So we introduced a new tag column for the logic flow table, which is basically key value pairs, providing help for ovn controller to process the logic flows more efficiently. The first use case is in-out port. The key here is in-out port, and the values for ingress pipeline is import, and for egress pipeline output. When the ovn-nosd fills such information in the match condition for import or output, it can add this information in the tags so that ovn controller can filter out non-local logic flows before parsing the logic flow strings. This would avoid a lot of processing waste on ovn controller. And the test result shows significant improvements with this approach. Now let's look at some echo optimizations, which is important for implementing efficient distributed firewall using OVN. Ingress policy example is allow IPs in address set A to access logic switch port in port group B, which has the match condition out port equals port group B and IP source equals address set A, basically what the picture shows here. And port group B can span across different nodes. On each node, there can be some of virtual interfaces belonging to port group B. So this is translated by OVN controller into m plus n plus 1 OpenFlow rules on a node. M is the number of local interfaces of port group B, and n is the number of IP addresses in address A. So n can be huge. And the red part is the scaling problem. There will be n number of flows in the red part. When any member of the address set is changed, logic flows referencing the address will be reprocessed currently. And before the optimization, reprocessing a logic flow will regenerate conjunction IDs. And that means all the m plus n plus 1 flows will be changed and deleted and reinstalled to OVS, which causes control plane latency unnecessarily, and which can also cause the data plane impact because MacFlow cache has a churn and it can cause a lot of upcalls. Now with optimization, we use UUID-based consistent conjunction ID generation, which means in most cases, conjunction ID won't change. And so only the flows corresponding to the added or deleted IPs of the address set will be updated to OVS instead of them. And further, we are working on the fine-grained address set incremental processing for the more efficient echo processing to avoid unnecessarily flow regeneration. So for all these flows, even if we preserve conjunction ID, but regenerate all these flows, still a high cost in OVN controller. And when the change rate is high, OVN controller can still be very busy just processing the address set changes. The goal is to only update the OpenFlow rules that's related to the changed member of the address set. And this work is still ongoing. Finally, I will talk about something about incremental processing. We all know that incremental processing is critical for OVN to scale, and we have achieved a lot over the years for incremental processing framework in OVN controller, in OVN NOSD, and even in the OVS-DB server in some cases. But here I want to talk about something we need to be careful about incremental processing. So let's have a comparison between the incremental processing and recompute. In terms of latency, if there's only small change, then we're sure that incremental processing should be much faster than recompute. But when the size of a change increases, let's say 50% of the total data has changed in one shot, maybe we cannot tell which way is better. And if there's 90% of data changed in one shot, we are almost sure that recompute should be faster than incremental processing each of the changes. And speaking of throughput, if we keep pushing the changes to the system and push to a limit, then we can also say that recompute should be better because reprocessing everything in one iteration is almost constant time, no matter how fast the change happens in the input. So this leads to some thoughts. Incremental processing is great for latency-sensitive system with small changes, but it's not necessarily good for system that tolerates high latency but requires high throughput with batch jobs. One example is if we must finish like 10K jobs within 1 minute, so one minute may be not enough for the scale and for recompute to finish any compute. But the size of job is really big. If we use incremental processing, that might not be achieved, depending on how efficiently a single change is processed in incremental processing. So the efficiency of incremental processing for a single change is critical for the throughput when the change rate is high. And it's valuable to have a capability to fall back to recompute when the change size is big. So when a big portion of the data is changed, maybe just recompute is better than incremental processing. And finally, incremental processing is complex and error prone. So we should do it cleanly, and we'd rather doing less than doing it wrong. Okay, this is all that I want to share. Thank you.